Okay, I've started the recording. And so here we go. All right, so here's another problem. This is a fifth degree polynomial function. And again, I have no idea how to factor this thing. But if I was smart enough to factor it, it would look like this. That's what it looks like when it's factored. Now, something I should mention here, I thought I had done that on this. Doggone it. It's an, oh, yeah, let me go back to that, see if I can find that last one we did. Oh, crud. Yeah, okay. Well, no, I didn't. Oh, well. Here's what this is. Just so you know what this means, where it says x plus 4 in parentheses to the second and x minus 1 in parentheses to the second. What that is this. Give me a second, I'll get my left hand out of the way. So notice where this says x plus 4 to the second power. In other words, that x plus 4 factor shows up 2 times. And x minus 1 to the second power, that x minus 1 factor shows up 2 times, right? So we at least know, if we look at it in its original form, we should be able to figure out its end behavior. So what is it? Is it up, up, down, 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 up, or up, down? So I'm being told up on the left, down on the right. Do y'all agree with that? Here's our chart again. It's odd degree, fifth degree, and the term itself is negative. Odd degree, the term is negative. Yep, it's up on the left, down on the right. Everybody see that? And so we can also find the zeros of the function, because it's been factored for us, right? Like if it was just this, we certainly couldn't see what the zeros are, but here it is factored. Now this is fifth degree. And remember, if it's fifth degree, if you write all of this stuff equals 0 and you can find all the solutions to that equation, there should be 5 solutions to that equation, right? However, there's really only 3 solutions. Do y'all see that? So negative 2 plus 2 is 0. So negative 2 makes the entire thing 0. Negative 4 plus 4 is 0. So negative 4 makes the entire thing 0. And positive 1 minus 1 is 0. So positive 1 makes the whole thing 0. That's all. There's only 3 zeros, but it's fifth degree. There are supposed to be 5 zeros. Well, that's because there kind of are 5 zeros, right? Y'all look, negative 2 is a 0. Negative 4 is a 0. Negative 4 is a 0 again. Y'all see that? That's just 1 0. Negative 4 is just a single number, but it happens 2 times. Y'all see? And the same thing happens with 1. 1 makes this factor 0, but 1 also makes this factor 0. So notice if you count each solution to this thing equals 0, each time it shows up, there's a total of 1, 2, 3, 4, 5 solutions, right? Yes. I will pretty quickly, in fact, starting with the next problem, I will not be factoring these for y'all. But as I've said, I don't know how to factor this. What I did, I cheated. I wrote this out and then multiplied it all together. And I could have multiplied it all together by hand. It would have meant I'd have to do x minus 1 times x minus 1, FOIL those together, right? Then I guess I could FOIL x plus 4 times x plus 4 all together. Then whatever I got from the x plus 4 all squared, I could multiply all of that mess times whatever I got when I did x minus 1 all squared. And then whatever I got there, I could multiply x plus 2 times all of that stuff. And then I could apply this negative sign, which would reverse all the signs. That said, I didn't do that. I typed this into Wolfram Alpha and let it tell me what it's equal to. So, but we're going to learn to find the zeros of a function like this, even though we don't know how to factor it. That's what we're going to be working on after this problem, okay? So hang with me a minute. But what I wanted to say here is there are sort of 5 zeros. It's just they're not all distinct. In other words, -2 shows up as a 0 one time. -4 shows up as a 0 2 times. +1 shows up as a 0 2 times. Altogether, 5 zeros show up. They're just not all 5 different numbers. Y'all see? At any rate, those are going to be our x-intercepts. And you can see that our y-intercept is -32. That's the constant term, right? So I can go ahead and say, notice I'm going by 4s here. So -4, 8, 12, 16, 20, 24, 28, -32. That's right there. That's our y-intercept at -32. And our x, up here on the x-axis, I'm just going by 1s. On the x-axis, we got -2 as an x-intercept. We got -4 as an x-intercept. And we've got +1 as an x-intercept. Now, we know the end behavior. Remember, it's up on the left, down on the right, because that's negative x to the 5th. So it's up on the left, down on the right. Now, here's where things are going to get a little bit sticky. And let me see if I've got, I always gripe at students who show up for the test without a pencil. And tonight, I actually need a pencil. And it seems like I might have one. Okay, so I'm going to use a pencil, so this is going to be light. You're going to have trouble seeing it. But I need something I can erase because I suspect I'm about to do this wrong. If I tried to play connect the dots the way I did with that last problem, y'all look. Follow my pencil here. I would come down. I'm going up on the left, so I'd come down and hit this x-intercept. I'd go through the x-axis and come up and hit this x-intercept, and I'd go through the x-axis, and I think I'm in trouble. Do y'all see why I'm in trouble? I got to hit this y-intercept down here. Do y'all see that? Well, how can I hit it? Because the only other place I'm ever going to cross the x-axis is here at +1. So if I come over here and cross the x-axis at +1 and finish going down, I'm going to miss my y-intercept. Y'all see that? But I can't miss the y-intercept. That's a point on the graph. Do y'all see what I'm saying? So something must be going wrong here. Let me erase this, and let's see if we can figure out what's going on and how to fix it. So obviously then, connecting the dots between the end behavior, the ends of the graph, may not be as simple as just hit the x-intercept, go through the x-axis, turn and hit the x-intercept and go through the x-axis and so on. Here's what's going on. Somewhere here, let me see what I do. I actually wrote this down, so somewhere here I should have it, but maybe I don't. That's par for the course. Okay. Because by the time we're this far into class, I've got papers just strewn everywhere. Here's the deal. What we're looking at is an idea called multiplicity. Multiplicity. Which also happens to be the title of a very bad Michael Keaton movie that you probably are all too young to have seen. But it's out there somewhere. Multiplicity, cool sounding term, but really it just means how many times does that number show up as a 0. So -2 only shows up one time as a 0 in this function, right? The factor that causes it to be a 0 only shows up one time. Then we're going to say that number -2 has multiplicity 1. -4, however, shows up as a 0 2 times. Does everybody see that? Then -4 has multiplicity 2. And +1 also shows up as a 0 exactly 2 times. Then +2 also has multiplicity 2. The multiplicity of a 0 determines what the graph does when it gets to that x-intercept. And here's the rule. It's a very simple rule. If the multiplicity is odd, so -2 only shows up as a 0 exactly 1 time, and 1 is an odd number, right? So -2 has odd multiplicity. It shows up as a 0 1 time. When the multiplicity is odd, the graph passes through the x-intercept when it hits that, it passes through the x-axis when it hits that x-intercept. In other words, when I hit, oh, sorry, we got to talk about -4 first, right? There's -2. -4 has multiplicity 2. If the multiplicity is even, it occurs as a 0 2 times or 4 times or 6 times. In this case, -4 occurs 2 times. Let me get rid of that. If the multiplicity is even, the graph does not pass through the x-axis when it hits that x-intercept. It bounces off. In other words, we know we're going up on the left end. I've got to come down and hit this x-intercept. But when I do, I don't pass through the x-axis. I actually hit that point and turn and go back up. Y'all see what I'm saying? It bounces off, sort of. I know that I've got to turn in time to come down and hit this x-intercept, -2, but it has multiplicity 1. 1 is an odd number. If the multiplicity is odd, then when the graph hits that x-intercept, it does actually pass through the x-axis. I don't know exactly where this thing is going to turn, but I do know it's got to turn in time to hit this y-intercept, right? So I'm going to turn and come up and hit the y-intercept. And of course, then I've got to come up and hit this x-intercept. Now that's the x-intercept +1. But +1 has multiplicity 2. 2 is an even number, which means, again, the graph does not pass through the x-axis. It's going to turn and go back down. And of course, that's good because we know it's supposed to be going down. It's supposed to be going up on the left, down on the right. We've hit all of our x-intercepts. We've hit our y-intercept, and we've passed through the x-axis at the x-intercept we were supposed to, and we've sort of bounced off that x-intercept at the 2 x-intercepts where we're supposed to. So I told y'all I was going to show you the graph of that last one. Let me show you the graph of this one. By the way, that last one, I didn't talk about multiplicity, and I just passed through the x-axis each time. But if you look back at your notes, you'll see that on that one, it was 4th degree, and there were exactly 4 different zeros. They all had multiplicity 1, which means it should pass through the x-axis at each one of those. But when you've got even multiplicity, like a couple of these had. So let me real quickly go to Wolfram, and I'll try to show you all this graph. And let me tell you what's going to happen when I do show you this graph. You're probably going to see that the top of the hump here and the bottom of the dip here, those may be wildly off. Like maybe this thing goes way, way down before it turns and comes up. Or maybe this thing goes way up before it turns and comes down. Or maybe it barely goes up at all before it comes down. Again, these points, this one, relative maxima and minima, we don't have a good way to find those with algebra. But I think you're going to see that our end behavior is correct, and we've got all the correct intervals sort of where the thing is decreasing, increasing, decreasing, and so on. You'll see that, so put a picture of that graph in your mind, and let's look at Wolfram. Let me stop sharing this. Let me see if I can get over to Wolfram and start sharing it. Okay, so let me put that function in, and I'm just going to, yeah, I'll just put in the whole big nasty looking thing. I could just put it in factored form, but I want you to see that when it's not in factored form that we got what we're supposed to get. Minus 8x to the fourth, minus 13x to the third, plus 22x squared, plus 32x minus 32. Hopefully I entered that correctly. Minus 8x to the fourth minus 13x squared plus 22x x to the third x squared 30. Yep, okay. So let's see if the graph looks like it's supposed to look. Okay. So we're going up on the left end. You can barely see that, but that's because they've chopped the graphs off. And if I went very much further, I might could make it a little bit better. Where did they chop it off? -4 and 1. What if I went from, maybe I can make that look a little bit better. The problem with trying to widen the x-axis is sometimes that makes it where you can't see what's happening on the y-axis. Let's see what happens. Yeah, that's what I was afraid of. See, it flattens it out so much you can't see what's going on the end. But you can see that it's going up on the left and down on the right. Let me just take that out. No help. That's because the computer usually does a pretty good job of picking the right sort of part of it to show you. So it's going up. Notice when it comes down and hits -4, y'all see where the cursor is. It's the x-axis at -4. Notice it doesn't pass through the x-axis. It bounces off and goes back up. But notice how when it hits -2, remember that one just had multiplicity 1, it goes right through the x-axis. It turns, it comes up, it hits the y-axis. Notice the tick mark there is at -30. It's at -32. It's crossing the y-axis. Comes up, it hits that x-intercept at 1, and notice it doesn't pass through the x-axis. That thing had multiplicity 2, and sure enough, it bounces off of it. And so that's pretty darn close to exactly the graph we drew. Do y'all see that? Again, I can't tell you what that point is or this point, and I don't know if it tells me that either. It might. Notice it says the roots. By the way, that's another name for zeros. The zeros of a function are the values of x that make it 0. The roots of a function, that's just another word that means the values of x that makes it equal to 0. -4, -2, and 1. Yeah, that relative maximum right there. So notice that's happening somewhere close to -3. The x-coordinate, I mean, is somewhere close to -3. They say that is happening at exactly the square root of 129 over 10 minus 17 over 10. What do you want to bet that that's like -2.8 or something like that? Somebody could just punch that into their handy dandy calculator, but maybe I'll just do that real quick just to show you what's going on there. So what did they say? 100. So let me try to do this and I'll tell y'all what it tells me. Square root of 129. Oh, no. Yep. Divided by 10 minus 17 over 10. -0.56. Let's see if that looks right. -0.56. -0.56. That's the relative minimum. See the relative minimum here, right there? The x-coordinate of that point is about -0.56. Like this thing actually told me the exact value of it, where it went. There. And then if you punch this one in, negative 17 over 10 minus the square root of 129 over 10, that would tell you what that x coordinate is of this point at the top of this hump, which looks like it's about negative 2.8 or something like that. I don't know, whatever. But again, we can't figure that out. The computer used calculus to do that. We don't have calculus at our disposal. But you can see the graph is pretty accurate. Oh, so back to our, let me stop sharing first of all. Oh, maybe I did. All right, so now we're going to take a look at what's going on in 3.4. This is where it, like, y'all may or may not like what we're about to do, but to me, what we're about to do is kind of cool, because we've just seen that these polynomial functions can be, here's what I'm calling 3.4. I think this is pretty close to the title. Whether it is or not, that's what's going on in the section. We're finding zeros of polynomial functions. Okay, so I think the best way to do this might just be to dive in and look at some examples. So here is a function, y equal x to the third minus 3x squared minus 13x plus 15. So remember, Grace, you asked me, are they always going to be factored for us? Well, this one is not factored for us, and I don't know how to factor it. And so the question is, can we still find its x-intercepts and draw a reasonable sketch of the graph? And so there's a couple of things we know without doing any math at all. We know the end behavior is down on the left and up on the right. We know that because the degree is odd, third degree, and the term itself is positive, x to the third. And if you consult your little chart, you'll see that the end behavior is down on the left, up on the right. We also already know that the y-intercept is 15. Everybody see that? Because remember, that's always the constant term. By the way, do y'all see why the y-intercept is always the constant term? Look up if you're looking down. The y-intercept is whatever point on the graph has 0 as its x-coordinate, right? Because every point on the y-axis has 0 for its x-coordinate. So to find the y-intercept, what you're really doing is plugging 0 in place of x and finding the y value that goes with it. But in a polynomial function, every single term except the constant term has x in it. And so if you replace all those x's with 0, you just get 0 minus 0 minus 0 plus 15, which does 15, right? That's why that happens. But at any rate, our problem is we do not know what the x-intercepts are. And as we've been discussing, I don't know how to factor this. And I truly don't. I'm not saying that hypothetically. I'm saying in real life, I do not know how to factor this. So I'm going to show you how to do something that is ultimately going to allow us to find all the zeros, which means all the x-intercepts for the graph. And that thing we're going to look at is called synthetic division. Some of you may have seen synthetic division before. Some of you may never have seen synthetic division before. But here's the idea. It turns out that just like you can divide one number by another number, you also can divide one polynomial by another polynomial. And I don't mean like we did in section 2.6 where you just put f of x over g of x and call it done. I mean where you literally do the division. One way to do that is with long division. And it's similar to how you do long division with numbers, but a lot more complicated. Sometimes you have to do long division. Sometimes synthetic division won't work. But synthetic division will work for everything we're ever going to need to divide polynomials for. And synthetic division, when it's available, when it will work, when you have a situation where it'll work, it's easy as a dog to do. Now, it's a pattern. It's just a little algorithm. It's a pattern. You do these little steps and then you just keep repeating the same steps till you get finished. But you've got to see the pattern. So my advice is on this first time through, don't take any notes. We're going to basically spend the rest of class tonight doing synthetic division. You're going to get lots of chances to take some notes. This first time through, just watch. Because I think once you see the pattern, it's real easy. But if you got your head down trying to write down what I'm saying and you miss the pattern, there's a lot of pointing and arrows and stuff. So here's how we do it. I've got this little, I don't know, sideways L. And I'm going to write some stuff here. 1, -3, -13, and 15. Okay, y'all tell me, where did those numbers come from? They're the coefficients of our function, right? Remember, what are we trying to do here? Well, we're trying to find the x-intercepts for the graph of this function. In other words, we're trying to find all the solutions to this thing equals 0, right? Okay, I've written the coefficients. That's 1x to the third, so I put a 1 there, minus 3x squared, so -3, minus 13x, so -13, plus 15, so I put positive 15. Okay, I'm going to put a 2 out here. Now, I'll talk to y'all about where I got that number from or what that number means, because you don't see the number 2 up here anywhere, right? We'll talk about what that means in a few minutes, but let's just do what I'm going to call synthetic division. When it's all over, we'll talk about what I've done. So I'm going to take this real slow so y'all watch real close, because this is how you do it every single time. You always start by bringing this first number down. The first number inside your little sideways L, which is 1, you bring it down below this bar. Y'all see that? Everybody with me? And then you multiply. You're going to multiply, and here's what you multiply. You multiply this number that's on the outside, in this case 2, times 1. Everybody agree that 2 times 1 is 2. You bring that number up diagonally under the next number. In this case, under the number -3. Everybody see that? Okay, now you do signed addition. In other words, look at these two numbers in this column, -3 and +2. I'm going to do -3 plus 2. Everybody agree that's -1, right? -3 plus 2 is -1. That goes below the bar. That's the entire process. Now we just keep doing those same steps over and over. So now that I've got -1 below the bar, I'm going to multiply 2 times -1. Everybody see? And 2 times -1 is -2. And I'm going to bring that -2 up diagonally under the next number, under the -13. Now I'm just doing signed addition. -13 minus 2 is -15. That goes below the bar. Everybody see how that's working? Everybody with me? So what do I do now then? Yeah, I'm going to multiply 2 times -15. Again, we just keep doing the same stuff over and over. +2 times -15 is -30. That goes under the next number. So I need to put it underneath that 15. And I do signed addition. 15 minus 30 is what? -15. That goes below the bar. Now I have run out of numbers. Do y'all see that? That means I'm finished. That means I've finished the synthetic division. Now the question is, what does all this gobbledygook mean, right? So let me write this in a clean way without all the arrows so we can talk about what it means. So we went through the synthetic division algorithm, and this is what we got. By the way, I put a little kind of a piece of a box or a little backwards L around that very last number, that last negative 15. There's a reason for that. So let me tell you what I've done, first of all, and how to sort of analyze what's going on here. What I have really done is I have done this division problem. I have done this division problem. I have divided the polynomial x to the third minus 3x squared minus 13x plus 15 by the polynomial x minus 2. Remember, x to the third minus 3x squared minus 13x plus 15, that's our function. We're trying to figure out what values of x make it 0. I have divided this thing, and notice, remember, these numbers, 1, negative 3, negative 13, and 15, that's the coefficients of this polynomial that's being divided. The thing that's being divided is called the dividend. And so its coefficients, 1, negative 3, negative 13, and 15, go inside here. The 2 that is outside here comes from our divisor. Remember, the divisor is the thing you're dividing by. And what goes out here is, notice this is negative to x minus 2. That's negative 2. I didn't write negative 2. I wrote positive 2. Do y'all see that? That's because the number that you write, y'all see here, the number you write outside that little sideways L is whatever number you would replace x with in the divisor to make it 0. And positive 2 minus 2 is 0. So I put plus 2. Another way to think about it, though, is if you want to divide by x minus 2, you put plus 2. If I had been dividing by x plus 2, I would have put minus 2, right? You just reverse that sign. So first of all, this kind of division is the only kind of division synthetic division can do, where the thing that you're dividing by is just x plus or minus a number. Like if I was trying to divide by x squared plus 3x minus 4 or something, I would have to learn to do long division for that. But as long as you're only ever dividing by x plus or minus a number, you can always use synthetic division. So now let's talk about what the result here, what all that stuff means. It means that when I did that division, my answer is x squared minus x minus 15 with a remainder of negative 15. So first of all, how do I know all that? Well, here's how I figured out what my answer is based on these numbers I got down here. Notice how in this original, when we started, we put the 1, negative 3, negative 13, and 15 in here. Notice the very last number, 15, that's our constant term, right? 15. Negative 13 is the coefficient of the first degree x term. Negative 3 is the coefficient of the second degree x term. And positive 1, of course, x to the third is the same as 1x to the third. Positive 1 is the coefficient of the x to the third power term, right? Well, the same thing's happening down here. The very last number, though, in this case, this negative 15, is always your remainder. So, you know, sometimes when you divide stuff, it doesn't divide evenly, right? Sometimes you have a remainder. Well, our remainder is negative 15. Then the next number to the left, that is the coefficient of the constant term. Negative 15 is the constant term of our answer. Negative 1 is the coefficient of the first degree x term, and positive 1 is the coefficient of our second degree x term. So you count up. Y'all see that from the right. It's always remainder, constant term, coefficient of the first degree x term, coefficient of the second degree x term, and if there were more, the next one will be the coefficient of the third degree and fourth degree and fifth degree x terms. So what we would say I have done here is I have done this division problem, and my quotient is x squared minus x minus 15, and my remainder is negative 15. Okay? I can prove to you that that really is the answer to x to the third minus 3x squared minus 13x plus 15 divided by x minus 2. To prove it, I would do this, and I'm not going to take the time to do it, but I'll talk to you about how you can see that if you want to. The way you check a division problem is this. If I was doing 14 divided by 3, 14 divided by 3 is 4 with a remainder of 2. Agree? Because, you know, if you did long division, 14 divided by 3, 3 goes into 14 4 times. 4 times 3 is 12. 14 minus 12 is 2. So 4 is our quotient. 2 is our remainder. And remember how you check a division problem? If we've done a division problem here and done it correctly, if I multiply my divisor, which is 3, times my quotient, which is 4, and I then add my remainder, which is 2, I should get our dividend, the number that was being divided back. I should get 14, right? And I will. 3 times 4 is 12. 12 plus 2 is 14. That's what we're supposed to get. So 4 with a remainder of 2 is the correct answer to 14 divided by 3. Everybody with me? If you wanted to prove that we've really done this division problem and done it correctly, then what you would need to do is multiply your divisor, which is x minus 2, times your quotient, and that's the numbers that come from the stuff to the left of that little box at the end. That was x squared minus x minus 15. And then you would add your remainder. In this case, I would add a negative 15. And if we've done division, and if this is the correct answer, then when I do all this, I should get this dividend back, x to the third minus 3x squared minus 13x plus 15, right? Yeah, I'm going to do it, but I'm going to do it real quick, okay? But just to show you, I'm going to distribute the x to all these terms. I'm going to distribute the negative 2 to all those terms. I'm going to combine the like terms, and then I'm going to add this negative 15, which means subtract 15. So here we go. X times x squared is x to the third. X times negative x is negative x squared. X times negative 15 is negative 15x. Now move over to negative 2 times x squared, which is negative 2x squared. Negative 2 times negative x is positive 2x. Negative 2 times negative 15 is positive 30. And then don't forget, we need to add a negative 15, and of course positive times negative is negative, so we need to subtract 15. So when I combine like terms, I got x to the third, negative 1x squared minus 2x squared is negative 3x squared. Negative 15x plus 2x is negative 13x. And 30 minus 15 is positive 15. So x to the third minus 3x squared minus 13x plus 15. That's what we started with, right? So we really did do a division problem. But really, the reason we're doing these division problems isn't just for the sake of division. So let me go back to this again. Now, let me write this, a clean copy of this again, because I keep gumming it up, and you can't erase dry erase marker, unfortunately. Or you can erase dry erase marker off a board, but you can't erase Sharpies off of paper. That's what I should say. So let me write it out again. Okay, so here's another thing I want y'all to see. So that function was, it was x to the third minus 3x squared minus 13x plus 15. That was our function. Remember, we're trying to figure out what values of x make this equal to 0. And we've done this weird little synthetic division thing. And so far, that doesn't seem like that helped us figure out what makes it 0. I want y'all to take a minute. If you got a calculator, you'll probably want to get it out, but if you're good at arithmetic, you can do it without a calculator. I want y'all to find f of 2. Find f of 2. In other words, plug 2 into this function in place of x and tell me what you get. It ought to just take a few seconds to do that with a calculator. Who said that? Negative 15? Now y'all all need to be as comfortable using your calculators as Grace is so you can figure that out as quick as possible. Negative 15. Now, that's right, because look, 2 to the third is 8. When I plug 2 in here, 2 squared is 4, and negative 3 times 4 is negative 12. When I plug 2 in here, negative 13 times 2 is negative 26, and then I got plus 15. And 8 minus 12 is negative 4. Negative 4 minus 26 is negative 30. And negative 30 plus 15 is negative 15. So that's f of 2. That's correct. It's negative 15. Y'all see this? Is it just coincidence that that last number there is negative 15? Remember, we put the 2 out here and did synthetic division? And when we did the synthetic division, we got negative 15, remember, for the remainder in that division problem. That just so happens to be f of that number, f of 2. Do y'all see that? That happens every single time. It's called the remainder theorem. So the remainder theorem says that when you do synthetic division on some function like this one, whatever number you put outside here, in our case 2, when you do the synthetic division, whatever you get for the remainder is exactly the same thing as you'll get if you plug, y'all look, if you plug this number into the function. Now again, that may or may not tell us something about how we're going to be able to find the zeros of this function. So let's go back to our function now. Then remember, we don't know how to factor this thing, right? But now we know how to do synthetic division, or at least now we've seen one example of synthetic division. So let's do some synthetic division. So we got 1, negative 3, negative 13, and positive 15. What if I put, oh no, let's put negative 3 out here. So if I put negative 3 out here, y'all make sure you see, technically that means I'm dividing this function by x plus 3, right? But I'm just putting the number negative 3 out here, and I'm going to do this. I'm not drawing all the arrows. So if you didn't catch the little pattern, just look up. I'll try to go slowly at least, but the arrows gum it up too much. So remember, the first thing we do is bring this first number 1 below that bar. What do I do now? Multiply negative 3 times 1. Negative 3 times 1 is negative 3. Where do I put that negative 3? Under this negative 3, right? Whatever you get when you multiply, in this case, negative 3 times 1 is negative 3. You kind of move that up diagonally. It goes under the next number. Everybody see that? And now I've got to do signed addition. In other words, negative 3 minus 3, which is negative 6. That goes below the bar. And now we do it all over again. We multiply negative 3 times negative 6, which is positive 18. I move that up under the next number. So now I've got negative 13 and positive 18. Negative 13 plus 18 is positive 5. That goes below the bar. And now we do it all over again. We multiply negative 3 times positive 5. That's negative 15. I move that up diagonally under the next number, and I do signed addition. This is just positive 15 minus 15, right? It's 15 minus 15, which is 0. Okay, so y'all tell me this. If I were to, based on what we see here, if I were to plug negative 3 into this function in place of x, what would I get for the y value to go with it? 0, because that remainder is f of this number, f of -3. Well, if plugging -3 into this function is going to make y equal to 0, then do you agree that -3 is one of the zeros of the function? Right? That's what a 0 is. It's a value that you plug in place of x that makes the whole thing equal to 0. So we're finding our zeros. We found the first one is -3. Now, this is third degree. There should be 3 zeros. I could now do synthetic division, y'all look, on this thing and try a number and see if I could make the remainder be 0. But remember, this is second degree, because remember how we count up? The last number, 0, is the remainder. So +5 is the constant term. -6 is the coefficient of the first degree x term. +1 is the coefficient of the second degree x term. In other words, what I'm looking at here with this 1 -6, 5 thing is I'm looking at x squared minus 6x plus 5. And remember how we said, y'all listen, this function, this polynomial, because we did a division problem, I put -3 out here. So what did I really divide this by? I put -3 out here. So what did I really divide all this by? By x plus 3, right? Well, remember, when we do a division problem, your divisor, which is x plus 3, times your quotient, which we see is x squared minus 6x plus 5, plus your remainder. Oh, wait a second, we didn't have a remainder. Do y'all see that? Has to be equal to the original function, right? So you know how I said I don't know how to factor this? Well, we're beginning to factor it. And here where I've got this 1 -6, 5, I could do synthetic division on that and try to find something that makes it 0. I don't want to. It's only second degree. Y'all see that? All we have to do is say, okay, well, I just need to solve x squared minus 6x plus 5 equals 0. And I don't need synthetic division for that. We do know how to factor that thing, right? So now that it's second degree, I can say, oh, well, it's got to start with x and x. The last two numbers multiply to be +5 and add to be -6. So it must be -1 and -5, right? Notice -1 times -5 is +5. -1 plus -5 is the middle number, -6. And so what makes those factors 0? +1 and +5, right? There are our 3 zeros. All 3 of them. It's third degree. It only has 3 zeros, right? They're all real numbers, so those are all of our x-intercepts. And if I wanted to sketch a quick graph of the function, I'm going to just scribble a quick one here. We got -1, 2, 3, and +1, 2, 3, 4, 5. And so our zeros are -3, +1, +5. Our y-intercept is +15. I don't know, that's up here somewhere. Maybe I'll go, 3, 6, 9, 12, 15. There's my y-intercept. We know the end behavior is down on the left and up on the right. Do you also agree that each time the graph hits one of these x-intercepts, it's going to pass through the x-axis? It's not going to turn and go the other direction, because this is third degree and they're exactly 3 zeros. And in fact, I can tell you now that this entire thing, that's what it looks like when it's factored. Every zero has multiplicity 1, so it's going to pass through the x-axis. At -3, it's going to hit the y-intercept. It's going to drop down pretty steep and hit that x intercept. It's going to pass through. the x-axis, it's going to come back up and hit this x-intercept at 5, and it's going to go right through, and there's our graph. And that's pretty close to the actual graph. So now there's only one thing left to figure out. All of this would have been impossible if I had not known to use -3 out here, right? Remember a minute ago, I put a 2 out here and we got -15, not 0, right? Everybody see what I'm saying? So that's the big trick. And this is what I told my Monday night class. I cheated because normally, look, there's infinitely many numbers in the universe. Only 3 of those infinitely many numbers will be zeros of this thing. So if you were just going to start guessing numbers out here and doing synthetic division and keep doing that until you finally got a remainder of 0, you could be here a long time, right? You might guess 1,000 numbers and never hit one that makes it 0. So there is a trick, and I'm going to show it to y'all. This is the important, to be able to find zeros of these higher degree polynomial functions, this is the important trick to know. I hate that example I have right there. Let me see if I can come up with a bit. I didn't want to show this one next, and I misplaced a couple things. Hang with me a second. Let's try this. So that's going to be, I could get Wolfram to do this faster for me. Y'all hang with me a second. I don't know why I'm going to do this by hand when I've got a computer and we're pressed for time. So hang with me a second. I'm not going to put this up on the screen because I'm just doing some scratch work for myself. So just hang with me. Of course, Greenville, y'all are seeing it on the screen because whatever my screen sees is what y'all sees. Let's just try that. Okay. The example I had, there's some weird stuff going on. We may have to do that one first next week. So let me write this out. Okay. All right. So here's our function. And we want to, let's just say we want to graph it. But that means we got to figure out the end behavior, the y-intercept. We've got to figure out the x-intercepts, right? So really, can we find the x-intercepts? Because at this point, for instance, we know that the end behavior is up on both ends. Do y'all agree? It's of even degree, 4th power. That leading term, that highest degree term, is positive x to the 4th. So the end behavior is up on both ends. And we know that the y-intercept is the constant term, which is -12. So really, we just need to know the x-intercepts. Okay. We're going to do some synthetic division to try to find those because, again, I don't know how to factor this. It turns out there are infinitely many numbers that you could plug in place of x that might make this 0. It turns out, though, that really there's only like a handful of numbers, maybe a double handful of numbers that might make this 0. There is a there's actually a little thing we can do. It's called the rational zero theorem, okay, which sounds pretty fancy. By the way, I think Rene Descartes is the guy we can blame for this one too. It turns out it's a simple idea, which is this. When you have a polynomial function like this, it turns out that there's only a small subset of numbers that have a chance to make this 0. I'm going to show y'all how to find that little subset of numbers. So here's what you do. You write your constant term, which is -12, right? Below that, you write your leading coefficient, which in our case is just 1. Do y'all see that? Remember, that's the coefficient of the highest degree x term. X to the 4th is the same as 1 x to the 4th. So you write out your constant term, whatever it is, write that down. Whatever the leading coefficient, if this had been 2x to the 4th, I'd have written a 2 here. Y'all with me? Okay, and here's what I want to do. I want to factor both of those numbers, and by what I mean by that is I want to write down the list of every possible factor of this number -12. So, for instance, I could do, we'll talk about the fact that it's negative in a minute. Let's just say the number 12. I could do 1 times 12, 2 times 6, 3 times 4, right? So 1, 2, 3, 4, and 6, and 12. Now, I could do +1 times -12, or I could do -1 times +12. I could do +2 times -6, or -2 times +6. +3 times -4, or -3 times +4. So in other words, any of these factors could be positive or negative, right? So that's what you do. You write out every single factor of that number. Always include your plus or minus sign to remind you that not only are 1, 2, 3, 4, 6, and 12 factors of that number, but -1, -2, -3, -4, -6, and -12 are also factors. We do the same thing for our leading coefficient. Now, when the leading coefficient is 1, that's pretty darned easy, right? The only stuff you can multiply to get 1 is 1 times 1, or -1 times -1. So the only factors of our leading coefficient are just plus or minus 1. So now, here's what the rational zero theorem says. It says the only rational numbers, now remember, rational numbers are numbers that can either be written as a fraction or an integer. Technically, they're just any number that can be written as a fraction, because an integer like 4 could be written as a fraction, 4/1. The only rational numbers that have a chance to make this equal to 0 are rational numbers that you can get by taking a factor of your constant term and putting it over a factor of your leading coefficient. Now, we'll see an example next week where that gets a little more complex, but when the leading coefficient is 1, y'all just watch, like literally watch what I'm doing here. You're doing 1/1, which is 1. You can do 2/1, which is 2. You can do 3/1, which is 3. You can do 4/1, which is 4. You can do 6/1, which is 6. Or you could do 12/1, which is 12. And remember, any of those numbers could be positive or negative. So notice if your leading coefficient is 1, then this list of all the factors of the leading coefficient, that is your list. Y'all see that? But see, if this had been plus or minus 1 and 2, so we'll look at an example of this next week, but just so you can kind of see what I'm saying, let's say the leading coefficient had been 2. Then your factors down here would be plus or minus 1 or 2, and then your possibilities would be 1/1, which is 1, or 1/2, which is 1/2, or 2/1, which is 2, or 2/2, which is 1, but I think we already found that number. You could do 3/1, which is 3, but you could do 3/2, which is 3/2. So you see what I'm saying? But starting out with a fairly easy case, these numbers are the only rational numbers that might make this equal to 0. And so, and notice there's 12 numbers here, right? Like there's 1, 2, 3, 4, 6, and 12, but there's also -1, -2, -3, -4, -6, and -12. But still, 12 is better than infinitely many. Do y'all agree? And so what you start doing is you start doing synthetic division, but you only ever use a number from this list. And I'll try next week to show you how you can make this a little bit more efficient. But tonight, I just want us to actually get to the finish line on one of these. Remember, when you do this, well, maybe I will show you one thing. So we're going to do synthetic division. And so here's our function. So inside our little sideways L, we're going to put 1, 4, negative 1, negative 16, and negative 12. 1, 4, negative 1, negative 16, and negative 12. And I'm going to use a pencil if I can find my pencil again, because the problem with this is when you're doing these by hand, you'll want to use pencil, because otherwise every time you mess up, you got to mark through it. You got to go to a different piece of your paper or a different part of your paper and do it over. Whereas if you use a pencil, if you try a number that does not give you 0, you can just erase a couple of rows and go again. You see what I'm saying? So let's try one that won't work. Let's say I tried, will 3 be big enough? Yeah, let's try 3. Now I can tell y'all it's not going to work because I kind of know in advance what's going to work, and I know that may be hard to see. But I just want to illustrate something here about even when you try one that doesn't work, it's not always a waste of time. So I'm going to go quicker with the synthetic division because we're about out of time. Bring the 1 down. 3 times 1 is 3. 4 plus 3, excuse me, is 7 below the bar. 3 times 7 is 21. Negative 1 plus 21 is 20. That goes below the bar. My lead's in pieces. 20. 3 times 20 is 60. That goes up under the negative 16. Negative 16 plus 60, is that positive 44? Is that right? I believe that's right. 3 times 44 is 132, maybe? Sure, we'll go with that. And negative 12 plus 132 is 120. So, okay, 3 didn't work because remember, we're hoping to get 0 for our remainder. We got 120. That means if I were to plug 3 into this function, y would be equal to 120, not 0. But here's why this wasn't a waste of time. Can you see? Hopefully you can see it well enough to see. Can you see that none of these numbers on the bottom row are negative numbers? There are no negative numbers down here. I got positive 1, positive 7, positive 20, positive 44, and positive 120. Anytime you put a positive number out here and do synthetic division, so notice I put a positive 3 out here. If you don't get any negative numbers on the bottom row, then that number, in this case 3, is called an upper bound for that function, which means that there is no number bigger than 3 that could possibly make this thing 0. So here's why that helps me. 3 is an upper bound because there was, when I did synthetic division with it, I didn't have any negatives on the bottom row. That means there's no number bigger than 3 that works, which means I can cross through the number 3 because I tried it and it didn't work. But I can also cross through the numbers 4, 6, and 12, and I don't have to try them. Y'all see that? Because no number bigger than 3 can work because 3 is an upper bound. So not a terrible idea when you start putting numbers out here and trying to find something that makes this 0. Not a terrible idea to start with numbers size-wise. They're kind of in the middle of your list because if it happens to be an upper bound, you get to wipe out, in this case, half of the positive numbers in your list. Y'all see what I'm saying? So at any rate, let me erase that and let's try to find these zeros real quick and then we'll get out of here. Hang with me. Erase. Erase. Synthetic division works a lot better on a whiteboard that you can just sort of run your arm across and erase it than it does on paper with a Sharpie. Okay, so let's try something else. Let's try 2. So here we go. I'm going to bring my 1 down. 2 times 1 is 2, so I put that under the next number, 4. 4 plus 2 is 6, that goes below the bar. 2 times 6 is 12. Negative 1 plus 12 is 11, that goes below the bar. 2 times 11 is 22. That goes under the negative 16. Negative 16 plus 22 is 6. 2 times 6 is 12. And y'all see that negative 12 plus 12 is 0, right? Everybody with me? Okay, so negative 2 is one of the zeros of that function. Now, what I could do is I could go back to this same thing where I've got the 1, 4, negative 1, negative 16, negative 12. I could try a different number from my list and see if it makes it 0. But don't do that. Remember, we saw that as you find these zeros, you're also sort of, without even meaning to, you're kind of beginning to factor the thing, right? So here's the deal. This is 4th degree, which means it has 4 different zeros. Or they may not all be different, but it has a total of 4 zeros. We just found one of them. Well, whatever this thing is down here, look, remainder, 6 is the constant term. That's 11 goes with our 1st degree x term. 6 goes with our 2nd degree x term. 1 goes with our 3rd degree x term. In other words, that's x to the 3rd plus 6x squared plus 11x plus 6, right? Well, that's only 3rd degree. So what if I do synthetic division on that thing and try to find something that makes it 0? Then the thing I'll have down here will only be 2nd degree. Do y'all see that? So as we find these zeros, we're also reducing the degree of this equation. Okay, so we tried 2. We found a 0. Now we're going to work on this thing, and let's try, what did we try a while ago? 3. Let's try negative 3, just for the sake of argument. So I don't know why I made this box so bulky. Bring the 1 down below the bar. Negative 3 times 1 is negative 3. That goes under the 6. 6 minus 3 is 3. That goes below the bar. Negative 3 times 3 is negative 9. That goes under the 11. 11 minus 9 is 2. That goes below the bar. Negative 3 times 2 is negative 6. And 6 minus 6 is 0. Okay, there's our second 0. We've only got 2 to go now. Do y'all see? Now, again, when you're doing this on your own, there's every chance that you're going to try some numbers that don't work. That's why you need to get comfortable with synthetic division. Once you learn to do it, it's super fast. And if you get one that doesn't give you 0, like I did, just erase that one and throw another one in there. But we found 2 of them, and this was 4th degree. So notice here it's 4th degree. I found a 0. That thing is 3rd degree. I found another 0. That thing is 2nd degree, right? That's 1x squared plus 3x plus our constant term 2. Y'all see that? Once you get it down to 2nd degree, don't keep doing synthetic division. The reason I say that is to find all the zeros of this, you're just hoping that most of your zeros are rational numbers, right? Like, what if your zeros turn out to be numbers like 2 plus or minus the square root of 3? Well, those numbers aren't going to be in the list because those are not rational numbers, right? What if a couple of the zeros turn out to be 2 plus or minus 5i? Well, those would be zeros, but they're not going to be in this list because they're not rational numbers. So we're hoping that no more than 2 of the zeros are not rational numbers. When you get it down to 2nd degree, in this case, we've got x squared plus 3x plus 2. Just set that equal to 0 and solve it. We know how to solve these. Even if you couldn't factor it, that means your other zeros aren't rational numbers. But even if you couldn't, you could use the quadratic formula and still find them anyway. This one can be factored. It's going to factor as x plus 2 times x plus 1, right? Because notice 2 times 1 is positive 2, our last number. 2 plus 1 is positive 3, our middle number. And so the zeros that go with those 2 factors are negative 2 and negative 1. Everybody see? So, hey, we got all our zeros. We got 2, negative 3, negative 2, and negative 1. And of course, that's enough to sketch the graph. So 2, negative 2, let's see this way, negative 3, negative 2. negative 1 and 2. So let's see if we can do a real quick graph job on this. I'm just going to scribble it pretty quick because I know we're out of time. So remember, it's positive x to the fourth, so the end behavior is up on both ends, right? The y-intercept is 12, so I don't know, maybe that's 3, 6, 9, 12 y-intercept. X-intercepts, we just found them all. -3, -3, -2, -1, and 2. So 1, 2. So -3, -2. Uh-oh, that doesn't look good. Let me double check. -2, -1, -3, -2. Oh, I knew something was wrong. What's wrong is our y-intercept isn't 12, it's -12. 3, 6, 9, -12. There we go. So, okay, our y-intercepts, -3, -2, -1. We hit our y-intercept and we come back up and we got the x-intercept +2. And I know I passed through the x-axis because I had 4 different zeros. It's 4th degree, so that means they all have multiplicity 1. Everybody see that? So this synthetic division, once you've done it some, you'll get used to it pretty quick. The video from Monday night has a couple of examples also where I was doing synthetic division. So those of you who weren't there that night, I'm going to post that video in our college algebra lecture videos also. I'll try to get these posted tomorrow. We're so out of time in this course, it's ridiculous. But when we come back from Thanksgiving, I'll try to do at least one more example of this where we do the synthetic division and find the zeros. And then we've just got to plow because there's stuff we're just not going to get to that basically I'm just going to have to, I'll be honest, tell you as we're working through the final exam review, okay, here's a problem we didn't get to, but I'll show you how to do it. And luckily, the stuff that we haven't gotten to is stuff that we can learn to do really quickly. I can also post videos from those sections from previous semesters. I'll try to do that. They may not be closed captioned because I've got some old videos saved, but they're saved in an old version of Blackboard and it won't let me download it so I can make them closed captioned, but it will let me post a link to them. So I'll try to post as many of those videos and I'll make sure I tell you what section and what topic it's over. So right now, homework wise, I told y'all you're not responsible for 2.7 and 2.8. We got to cover what's in on the final exam, which is 2 problems total from those 2 sections. But I'm not going to hold you responsible for that homework. We didn't cover the section. And also the chapter 4 homework. We may yet get to a little bit of that in the first part of class Thursday after Thanksgiving. But I doubt we're going to get to enough of it that I'm going to require you to do those sections of homework. It'll be more, here's what you need to know how to do and practice some problems till you can do those things for the exam. So that's where we are. Y'all have a great Thanksgiving. I'm sorry we're so rushed. Again, I moved too slow at the beginning of the semester, and you know, it is what it is. We'll get through it. I'll make sure that y'all are well prepared for the final exam. And hey, we're on Thanksgiving break. Let me hit. We will have class Monday. Those of you who are in the Monday class, we do have class Monday. Wednesday of next week, we will not. Our school is closed. We close for Thanksgiving Wednesday and Thursday classes. So the building won't be open. I couldn't get in myself. So otherwise, I'd love to come up here and give y'all a Thanksgiving lecture, but can't do it. So, you know, if you're dying for class, just look at some of the video lectures I'll be posting and just watch those and pretend like you're sitting in class or something. If you're into that kind of thing, like if you're into like sadomasochism or whatever that would be an example of.
What is the take-home assignment
The take-home assignment will be given to you next week, and you'll have to turn it in the night you come to take the final exam. So you'll have a week to do it.
Wait, so
Yeah, I'll be giving it to you, the take-home assignment that counts as test 3. I'll give it to you when we come back from Thanksgiving. You'll turn it in when you come to take the final exam the following week. Does that make sense?
yeah, you just said next week, and I was like, wait, that's.
The next time we meet, I'm sorry. Yeah, if I said next week, the drugs are taking effect. I meant the next time the class meets, I'll give it to you. The week after Thanksgiving. Sorry.
Can you just email me whenever you drop my test?
Yes, and if you don't get an email from me in the next day or two, send me an email and say, don't forget to put my test in there, because I very well could forget, but I'll try to remember.
Yeah, I'm not in a rush, I'm gonna study.
Well, I've got another student who I think is going to be taking the makeup exam tomorrow, and so hopefully if I come up to pick hers up, I'll remember to drop yours off, you know what I mean?
All right, thank you.
Okay. All right, let's see what we got going.